we're going to look at angular momentum and rotational kinetic energy definitions today. So our example will be this girl. She's an ice skater, and she's twirling in a circle right now. And in a little bit, she's going to pull her arms and legs in real tight to her body, and she's going to spin much faster. So why does that work? Well, it's actually a conservation of angular momentum idea. Okay, but let's at least take a look at our definitions. Okay, in our previous video, we did look at, force is equal to mass times acceleration, and we translated that into torque equals I alpha. So again, our Newton's second law being applied here, and of course Newton's first law in the moment of inertia, which is given the letter I. Let's take a look at definitions for momentum in angular sense. Well, we know momentum, linear sense, P is a vector, is equal to mass times velocity. And the reason it's a vector is because mass is a scalar quantity multiplied by a vector. Well, we give the letter L, okay, for angular momentum, and let's translate that now. M is now going to be the moment of inertia, I, in our example, and we translate V as omega, which is angular velocity. So, and that's something we did in our previous chapter. We looked at angular velocity in terms of velocity. So in our previous chapter, chapter 6, we said that momentum 1 must equal momentum 2. So the beginning momentum before something happens must equal momentum after something happens. Well, if we translate that into our angular stuff, that means L1 must equal L2. And these are actually vectors as well. We'll talk about that more in class to give you an idea of where that points. You're going to see that that points perpendicular, okay, to the rotation. But we'll deal with that later. So what does this translate into? Well, let's plug in I and W every time I see L here. So we're going to have I1 omega 1 equals I2 omega 2. Okay, now let's put this in perspective of our girl who's rotating here. So let's say she's spinning around. She presently has an angular velocity of some kind of W, we'll call it W1, and the position of her body, her arms out and her legs are out, she would definitely have an I1. It's not easy to calculate. She's not a regularly shaped object, so we would need a more complicated program to do that, but we can at least conceptualize it today. So she has a beginning moment of inertia. She's going to pull her arms in closer to her body and her legs closer to her body. We know that moment of inertia depends on the radius squared. So what's going to happen is her moment of inertia is going to go down. So I2 she's going to create, and therefore her angular velocity has to change. Now if we use this equation here, we've got I1 omega 1. When I2 goes down, we must see an increase for our angular velocity in order to make that equal to our beginning angular momentum. So, and that's how that works. So because her moment of inertia decreases as she pulls her arms and legs closer to the center of her body, her moment of inertia goes down. Therefore, her angular velocity must go up. So it's really a conservation of angular momentum that we're witnessing every time we watch the Olympics and we see these incredible skaters do what they do. Now finally, she must have some rotational kinetic energy. All things that are rotating have to have some kind of rotational kinetic energy. Well, in the linear sense, we say kinetic energy equals 1/2 mass times velocity squared. Okay, now if we translate that into kinetic energy rotational, and often what I do is I just put a sub r there to differentiate. Okay, so I'll have 1/2, and m is now I, moment of inertia, and v is now omega, and we'll put a squared on that. So our rotational kinetic energy equation is 1/2 I omega squared. You're going to find that the kinetic energy beginning rotational for this ice skater, so we'll say kinetic energy 1, okay, is going to be less than kinetic energy too. So once again, we're going to see that kinetic energy is not conserved. Okay, so don't panic. We are not violating any laws of conservation energy here. As she pulls her arms in, she's actually got to do work to do that. And when she pulls her legs in closer to her body, she's doing work. So when we say kinetic energy is not conserved, that doesn't mean we've created energy. So we're going to take kinetic energy 2 minus kinetic energy 1, and these are all rotational. That's going to equal the work that this ice skater does on her body as she moves those legs and arms in closer to her body. Because it's going to take some force to do that, because their natural tendency is going to be to go away from the circle. So we have to pull those in. And that's how we handle angular momentum and rotational kinetic energy.